All right. Hello, everybody, and welcome back. Today we're going to be doing section 4.2. This section is all about exponential functions. Let's get started. I'll pull up the slides and we'll get right into it. All right. All right, so section 4.2, here's the overview. We're going to start by just talking about the notion of a multiplicative comparison. We've looked at additive comparisons before, but I want to talk a little bit about multiplicative comparisons. Then we'll talk about proportionality. We're going to review some of our fundamental intuition of multiplication and exponentiation. Then we're going to get the definition of an exponential function. Then after that, we're going to talk about the characterization of an exponential function, which is essentially a property that defines an exponential function. So we'll see that there. We'll take a look at the graph of an exponential function, talk briefly about how to graph transformations of these exponential functions. Then we're going to talk about a very special number, the number e, and the natural exponential function. Then we'll finish up by talking about how to manipulate exponential equations, and we'll take a look at a geometric interpretation of those solutions as well. All right, so let's talk about multiplicative comparisons for a minute. Earlier in the course, when we were comparing quantities, we would find the distance between them and we would consider their order, which one came earlier on in the real number line, right? So sometimes instead of comparing quantities by how far apart they are, we want to know how many times as large one is than the other. So that's what's called a multiplicative comparison, looking at how many times something is as large as another thing. So you're comparing like the how they scale together. That's basically the idea. And I've got this example here that I want you to try at home. This is a good motivating example for what a multiplicative comparison can tell you. All right. So let's say two trees are planted and we compare their growth after 1 year. One tree grew from 2 feet to 4 feet, and the second tree grew from 3 feet to 5 feet. So, my question to you is which tree grew the most? All right. So, think about this for a minute, ponder it a bit, and then you know what you got to do next? You got to verbalize something. Say something out loud to give your brain that audio feedback to help you process things. All right. And now try to work it out on your own. See if you can figure out which tree grew the most. And then we'll talk about it in just a moment. All right. So let's look at something simple first. One thing I notice is that the first tree, it grew from 2 feet to 4 feet. So it increased its height by 2 feet. The second tree grew from 3 feet to 5 feet. So it increased its height by 2 feet as well. So they both grew the same amount of feet. They added 2 feet to their height, right? But here's the interesting comparison. The first tree doubled in size. It went from 2 to 4 feet. Whereas the second tree did not double in size. The second tree grew by a factor of 1 2/3. So here's a situation where a multiplicative comparison is a little more informing than an additive comparison. They both grew the same amount, but the first tree grew faster. The growth rate of the first tree was greater in this case. So that's one of the reasons that a multiplicative comparison can be a little more revealing about the behavior of a certain situation. All right. So now let's talk about proportionality, and we'll just start with a definition. Two quantities x and y are said to be proportional if there is some constant k not equal to zero, such that y is equal to kx. So in other words, two quantities are proportional if one is a scalar multiple of the other, and that number k is what's called the proportionality constant. This is very similar to what we explored when we were talking about vectors back in chapter one, and we said that two vectors were parallel if they were scalar multiples of each other. Another way of saying that is that those two vectors are proportional to each other, because you could take one, multiply it by some constant k, and that would get you to the other vector, right? It would stretch to or compress to that other vector. So that's what proportionality really means, that you could basically stretch or compress something into the other thing, the other quantity. Here's some examples. For example, we could say 28 is proportional to 7 because 28 is 4 times 7. And in this case, the proportionality constant is 4, k equals 4. 3 is proportional to 81 since 3 is equal to 1 over 27 times 81. And here the proportionality constant is 1 over 27. 2 pi is proportional to pi because 2 pi is 2 times pi. And here the proportionality constant is 2. So those are some examples of proportionality right there. Okay, now that we've kind of got our mind in the multiplicative mindset, right? Let's talk or let's review our fundamental intuition of multiplication. So you might remember this from chapter 1, but we talked about how multiplication stretches or compresses quantities, right? We saw it in chapter 1 when we were talking about vectors, like I just mentioned now. We saw it in chapter 2 when we were graphing transformations and we were doing vertical and horizontal stretches and compressions. Um, and I just mentioned this a moment ago, but two quantities are proportional if they can be stretched or compressed to one another by some constant multiplying factor. Now, very often we want to investigate what happens when we repeat the stretching or compression process. So if we wanted to repeatedly stretch, what operation do you think that could be? Ponder that for just a moment. If I wanted to repeatedly stretch or repeatedly compress. Well, if you said exponentiation, then you would be right. You can interpret exponentiation as a repeated stretching or compression process, repeatedly applying that stretch factor or that compression factor. So for example, let's say we start with a quantity C and we want to double it. Then we want to double that result and then double that result and so on and so on. So in other words, we want to repeatedly multiply by 2. Doubling it the first few times is going to look like what you see over here. So here C has been doubled. Then we're going to double that result. Then we're going to double that result. And we could keep going like so. And this is using an exponent, right? This exponent in this case is kind of counting how many times we're applying that stretch, right? Or indexing how many times we want to apply that stretch. And since we had talked about how our understanding of exponents can extend to rational and irrational numbers, because exponentiation is continuous over the real numbers, we can talk about quote unquote doubling by partial amounts. So for example, these exponents don't need to be whole numbers. They could be any real number and it would be fine, all right? That's the basic idea. So now that we're kind of thinking about this notion of stretching or compression and doing that repeatedly, let's define what an exponential function is. Oop, come on, there we go. Okay, so what is an exponential function? An exponential function is a function of this form, c times a to the x, where c is not 0, this base, is positive and also not equal to 1, right? This a is not equal to 1, and we'll see why in a few minutes, and then we'll also see why in the next section. So the domain of any exponential function is all real numbers. You can plug in any real number for x. And this base a is what we call the growth factor. Or sometimes we'll call it the scaling factor. It's like what you're scaling things by. C is what we call the initial value in this case, because if you remember, initial values are what you get when you plug in x equals 0. So if we plug in x equals 0 to our function, we get c times a to the 0, which is just c times 1, which is c. So this c factor, that is the initial value of the function, all right? A couple examples and counterexamples. Here's an example of an exponential function, 2 times 5 to the x. But this is a non-example of an exponential function because here that a value is -2, and -2 is negative, and we require that a is a positive number. So this would not be an example of an exponential function. All right, a has to be positive and not equal to 1. Now, intuitively, f of x is the result when you scale c by the value of a x many times. So basically, you're going to repeatedly multiply by a in some sense or another. All right, so that is the definition of an exponential function. Now let's talk about this important property, the characterization of an exponential function. Um, if you remember from earlier when we were talking about lines, the notion of a characterization of a function is a defining characteristic. And what that means is if you witness this characteristic occurring, then you must have this type of a function. And if you have this type of a function, then you must witness this behavior occurring, all right, this characteristic. So here is what that behavior is for an exponential function. F is an exponential function if and only if for all real numbers x, there is a positive number a that's not equal to 1. such that f of x plus 1 divided by f of x is equal to a, or maybe a little more intuitively, f of x plus 1 is equal to a times f of x. So what this means is, well, this. So this ties into this bullet point. It means that the ratio of integer consecutive outputs is constant. So if you go one step forward in your input and then you divide those results, you're always going to get the same number. But another way to write this is that f of x plus 1 is proportional to f of x. So what that means is if you want to get to f of x plus 1, you can take f of x and multiply it by a. Remember, these are outputs, right? So if I want to get the output at x plus 1, I could just take the output at the output at x and multiply it by a. That is characteristic of an exponential function, okay? So if you witness that behavior, you've got an exponential function. All right, let's prove this. So this is a pretty straightforward proof. It's kind of nice. We're going to prove that there's actually a defining characteristic of an exponential function. This is an equivalent statement, so we've got to do both directions. So first we'll suppose that f of x is an exponential function. Then by definition, f of x has this form, right? C times a to the x. Then we're just going to look at what f of x plus 1 is. So f of x plus 1 is c times a to the x plus 1. And that's equal to c times a to the x times a by properties of exponents. I'm just going to shift this a to the front for a minute to emphasize that now we have this expression, but c times a to the x is f of x by definition. So what we've now shown is that f of x plus 1 is a times f of x. Done. So we're done with that part. Now let's go the other direction. Let's suppose that this ratio here is equal to a, and a is positive and not equal to 1. Then for any non-zero c, we can write this. This is equal to a. We're going to multiply by a clever 1 here. We're going to multiply by this, c times a to the x over c times a to the x. We're going to move this a into the numerator like so, and then combine these expressions using properties of exponents, just like that. And now what we're going to do is we're just going to compare numerators and denominators. So check out this numerator here, f of x plus 1, c times a to the x plus 1. And then look at the denominator, f of x, c times a to the x. So as a result, this means that f of x is equal to c times a to the x, which means that f is an exponential function. There you go. So that is the characterization of an exponential function. Okay, let's do an example here. And this is one that I do want you to try on your own. What we've got here is we've got two tables, two functions, f and g, and I want you to determine whether the functions are linear, exponential, or neither using the characterization of an exponential function or the characterization of a linear function. All right, so think about that for a moment. All right. Say something out loud. Remember, you don't have to say it to anybody. You can talk to yourself, but if someone's around, you can talk to them and they might think you're weird, but that's okay. All right. And now try to work it out. See if these are linear, exponential, or neither. And we'll do it together in just a moment. Okay. All right, so let's focus on this function first, the function f. And in this case, we're going to look at the consecutive differences. So here I've got a table of what you get when you do the consecutive differences. So we're going to do 4 minus 7, and we get negative 3, right? 1 minus 4, and you get negative 3 also. Negative 2 minus 1 is negative 3. Negative 5 minus negative 2 is negative 3, and negative 8 minus negative 5 is negative 3 again. So what we're witnessing here is that the consecutive differences are equal, and they're equal to negative 3. So this function satisfies the characterization of a linear function, and therefore it must be a linear function. That also means that it can't be an exponential function because you can't be both linear and exponential. So this is a linear function by the characterization of linear functions. Now let's look at g. Let's look at the function g. And here we're going to investigate the consecutive ratios. So we're going to do 1/3 divided by 1/9. We get 3, right? Flip and multiply, we get 3. 1 divided by 1/3. Well, how many times does 1/3 go into 1? It goes in there 3 times. Uh, 3 divided by 1 is 3. 9 divided by 3 is 3. 27 divided by 9 is 3. So here's a situation where the consecutive ratios are equal. And every time we divide these consecutive outputs, we're getting the same number 3. So this satisfies the characterization of an exponential function. And in fact, this is the growth factor. This is A. That's the base A in that case. Oh, one thing I forgot to mention, going back to this function here, this is the slope. So this is the slope of that line. If you wanted to graph the line or wanted to write the actual form of the line, this is what you get right there. Yeah, once you know an initial value and you know a scaling factor, in this case, you can construct the formula for the exponential function. All right, okay, so now we've seen the characterization. Let's talk a little bit about the graph of an exponential function. And this is one that I want you to try on your own, first by just plotting some points, okay? So I want you to try to graph 3 to the x, and just start by plugging in some points. Maybe some good points are -1, 0, 1, 2, and 3. Try to do that, okay? So you can ponder it for a minute, give yourself some verbal feedback, talk to yourself, talk to your friend, talk to your dog. Right. And now try to work it out on your own. Try to just make a rough sketch by plotting those points and see what you get. Okay. Now let's take a look together. So here I've got a table of values, and then here is the graph of that function. So what you'll notice is that, well, there's a few things to notice. We're going to talk about this. Let's just start at 0 for a minute. When I plug in 0, 3 to the 0 is 1, and that's why we're getting that. That's that initial value, right? In fact, this actually is the graph of that function g that we were looking at earlier. Maybe I should relabel this as g just to be there you go. Call that g. This is what that graph looks like if you were to connect it with a continuous line. Oop, there you go. So when x is 0, you get 1. When x is 1, you get 3 to the 1, which is 3. When x is 2, you get 3 squared, which is 9, and so on and so on. So as x is going this way, the graph is shooting up to positive infinity really fast, actually. It's getting there really, really fast. Now, as x gets negative, as x goes that way in the negative direction, then the values are getting smaller and smaller, right? So think about this, 3 to the -1, that's 1/3. 3 to the -2, that's 1/9, smaller, right? 3 to the -3 is 1/27th, even smaller. So as x goes to negative infinity, the values of 3 to the x are getting smaller and smaller and smaller, closer and closer to the number 0. And in fact, ooh, I think I had this on another slide. I do have it on another slide. Where is it? Uh, Okay, I've got it kind of written on another slide, but what I'm really trying to get at here is that the limit as x goes to negative infinity of 3 to the x equals 0. So it's kind of plateauing down to that line, oops, sorry, plateauing down to that line 0. And the limit as x goes to positive infinity of 3 to the x is positive infinity. It's shooting up really, really fast, okay? Another detail here. This does have a horizontal asymptote. So in this case, the x-axis, that line y equals 0, is a horizontal asymptote. And this is a situation where the function will actually not cross that horizontal asymptote. Maybe to give you some reasons why, try to think of anything you could raise 3 to get 0. Think about it like that. You could try any positive number, you're not going to get 0. You could try 0 and you're just going to get 1, right? You could try any negative number and you're still not going to get 0. So it doesn't matter what real number you put in, you will never get 0. In fact, you're always going to end up with a positive result. That's the basic idea. Okay, now let's flip things around a tiny bit. I want you to try to graph this one now. So this is the graph of the exponential function. I'm sorry, this is the function 1/3 to the x, which we can rewrite as 3 to the -x using properties of exponents. So try to do this one on your own. You can either plot points or you can maybe be a little clever. We'll talk about that in a minute. So think about it for a minute. All right. Now verbalize something to help you process your thoughts. and then make a little sketch, and we'll do it together in a moment. All right. So, a couple things. Let me just show this slide. I went ahead and plugged in points so we can see what it looks like point-wise. Um, Maybe I'll start with that, and then I'll talk about another clever way you could imagine this as a segue into what we'll talk about in a couple of slides here. So again, just plugging in points. If I plug in -3, then what I get is 3 to the negative -3, which is 3 to the 3, which is 27. That's like way up here somewhere, okay? If I plug in -2, this negative is going to cancel that negative with the -2, and it'll give you a +2. So you have 3 squared, which is 9, right there. When x is -1, 3 to the 1 is going to be 3. And then again, when x is 0, you get 1. And then as x gets bigger, these numbers are now getting smaller. That's because the growth factor in this case is less than 1 in size. So things are shrinking. This is like you're repeatedly multiplying by 1/3. So imagine like taking a third of something, and then a third of that, and then a third of that, and then a third of that, and then a third of that. And you keep doing that, right? Well, if you keep doing that, you're going to get smaller and smaller and smaller. You're going to decrease each time. That's what's going on here. Now, maybe a more efficient way of imagining what this graph was going to look like is using transformations, which we'll talk about in a few minutes here. This is the graph of 3 to the x reflected across the y-axis, right? It's a horizontal reflection across the y-axis right there. Hold on 1 second here. 1 second. All right, there we go. Sorry about that. Just checking a technical thing there. Oh yeah, and then last but not least, you still have that horizontal asymptote. You're not going to get 0 by repeatedly multiplying by 1/3. You'll always have a tiny quantity, no matter how big x gets in size. All right, so here's just a comparison of some graphs of exponential functions. For example, this is the graph of 2 to the x. This is the graph of 4 to the x, and so on. So one thing you can see is that as the base increases in size, the graph gets steeper when you're bigger than 0, right? And it gets steeper very, very quickly. You could just imagine the base getting larger and larger. We're going to look at it on Desmos in just a minute. But this is one of the reasons people talk about exponential growth. Exponential growth is incredibly fast. Things blow up very, very quickly. And the bigger the base, the faster it blows up. As the base decreases a bit, notice it starts to shallow out. This is actually the graph of 1 to the x. And we do not consider this to be an exponential function. You can kind of see why. I mean, 1 to anything is just going to be 1. So we don't consider this an exponential function. This is a constant function. So we exclude it from the idea of exponential functions. But it's included here just so you can kind of compare what's happening. This is 1.5 to the x. And yeah, now if x is, or sorry, if the base, if that scaling factor is less than 1 in size, then you get stuff that looks like this. It's decreasing, right? Decreasing. So let's talk about some of those characteristics. Yeah. When a is greater than 1, then the graph of a to the x is strictly increasing. So as the exponent x gets larger, the number of times we multiply increases, and we're stretching those results up, right? Stretching them up. But if a is less than 1 and greater than 0, then we get a strictly decreasing graph. Again, because now you're repeatedly multiplying by something that is less than 1 in size. So you're going to be decreasing the value every single time. We can also see from these pictures that the domain is all real numbers, right? You can plug in any x value, no problem. And the range is actually 0 to infinity. So the range is 0 to infinity, but not including 0, right? You can never achieve the value 0 by plugging in something to these exponential functions. All right. Now, if you start shifting things around, all bets are off. You can do all sorts of stuff, right? Okay. Now let's play around with Desmos for a minute. If you want to follow along, you can. You can follow that Desmos link. Let me pull it up here. There we go. Okay, there we go. Okay, so what I've got graphed here is the graph of y equals b to the x. So b is our base in this case. And here right now I've got b equals 2. So look what happens when I increase b. Yeah, notice how much steeper it's getting really, really quickly. Really, really quickly. Let's go all the way to base 10, right? B equals 10. This grows really rapidly. I mean, when x is 1, 10 to the x is going to be 10, right? And then when x is 2, just by stepping over to here, well, 10 squared is 100. So just going from 1 to 2, you're now at 100. That's a huge increase, right? That's why exponential growth is, it blows up, right? Another thing, look backwards, right? So as x increases in the negative direction, this thing is plummeting down to 0, but never quite touching it. You can zoom in as close as you want, and it won't ever touch it. It'll just get really, really close. And you can see that as the base increases in size, it gets a little bit steeper, right? So as I go from a lower base to a higher base, it gets steeper. Now, let's look at what happens when b is equal to 1. Let's go down here. See, as we get closer and closer to 1, it's leveling out, not nearly as steep. And then, of course, when we get to 1, horizontal line, it's constant. 1 to any power is just 1, so it's just a straight line, right? Horizontal line. Now let's decrease the base. Let's make the base less than 1 in size, think. And now you can see that you've got that decreasing behavior. So now the graph is going to be decreasing as x goes to positive infinity, again, because you're multiplying by a number smaller than 1. And as b gets closer and closer to 0, gets more eccentric, just like that. Oop, there we go. Right about there is about as far as I can go with this step, right? And then 0 is just 0, right? 0 to anything is 0. 0 to the 0 is, well, indeterminate. You'll talk about that in Calc 1. All right, or Calc 2, one of the two. So let me just reset that. You can play around with that more if you'd like. We're actually going to look at this again in the next section when we talk about logarithms, so we can see how logarithms compare to exponential functions. Maybe this is a bit of a tell. For any of you that play poker, this is a bit of a tell. You can kind of figure out what the logarithm is going to look like. All right. Okay, let's get back to the slides. Let's talk briefly about graphing transformations of these functions. And the thing I want to say right off the bat is this is going to behave the same way it behaved back in chapter 2 when we first learned about transformations of graphs of functions. This is just applied to specifically to exponential functions. So I want you to try this one on your own. See if you can do this one. Graph this function. Oops. Graph this function by considering transformations of the parent function 3 to the x. Think about it for a minute. Right. Now, say something out loud. Maybe tell yourself what the transformations are. All right, and now work it out. Try to graph the resulting graph. Try to sketch the resulting graph. We'll do it together in a minute. Okay, here we go. So this is the parent function here, 3 to the x. This is going to horizontally reflect it across the y-axis, and then this is going to shift it up by 1. So here's the first transformation. We get a reflection across the y-axis, so this basically goes like that, and you get this. Now we're going to take that whole thing and shift it up by 1, just like so. So this is going to go up by 1, and it's going to carry that asymptote with it, right? That asymptote is part of the sketch. So the asymptote will also go up by 1 unit to kind of go with the graph. And that's the basic idea. Other transformations are similar. You've got a couple of questions on the homework about this, but it's really just the same thing that you learned back in chapter 2, just applied to exponential functions. All right. Now we got to talk about a very special number. I always like saying this because it's kind of funny. The number e. So it turns out that there is a very special best base to use for an exponential, and that base is Euler's number, the number e. All right. Oh yeah, this is pronounced Euler, by the way. And that number e is the base that's used in the natural exponential function, which we're going to talk about in like 2 slides. So one thing, the number e is an irrational number. It is transcendental as well, so it's not an algebraic number. And it's equal to this, but it's irrational, so it goes on forever. There's no continually repeating pattern. It's irrational. but roughly speaking, E is about 2.718 for rounding purposes or truncation purposes. Now, why am I calling it the best base? You'll learn more about that in Calc 1 and Calc 2, but yeah, I guess put succinctly, it's the best base to use because the natural exponential function is the only function that's equal to its derivative. That won't make sense yet, but it will make sense when you get to calculus 1 and you will prove it in calculus 1 or 2, all right? But just know that there is a best base to use, and that best base is E, okay? Now, how can we write this number in more of a closed form? There's a couple of ways to do it, but it requires calculus. So I'm just going to leave you with these two definitions of E. Here is one where E is written as a limit, and here is one where E is written as the upper bound of an integral. All right, so you'll talk about this limit in Calc 1 and 2. You will talk about this integral in Calc 1 and 2, and you'll actually prove both of these results in the calculus sequence in Calc 2, I believe. So yeah, that is the number E in like a closed form if I didn't want to write out the decimal representation. Okay. Now, that weird number, 2.71818, yada, 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 that forms the base of the natural exponential function. So the natural exponential function is the function that has e as its base, the exponential function that has e as its base. So e to the x. If you ever see e to the x, we call that the natural exponential function. And that's it. Now that we have it, we're allowed to play with it. Let's talk about manipulating exponential equations. And to do that, we're going to get this really helpful proposition, and then we're going to use it a few times in the next few examples here. So here's the proposition. Let A be positive and non-unital, so not equal to 1. Let M and N be real numbers. Then M equals N if and only if A to the M equals A to the N. Okay, now I want you to just ponder this for a minute before I read the rest. Ponder that for a sec. Okay. Now, what I'm really saying is if you've got an equality, if you have an equation like this, then you can exponentiate both sides with the same base. So if you have an equality like this, you can raise both sides of that equation with to a power where the base is a, whatever valid base you want to use, right? You could use 2, you could use 1.9, you could use e, you could use any positive a that's not equal to 1, and that will work. Okay. Now this forward direction, this is an equivalence statement, so they're interchangeable. You can go back and forth. Okay. Dang it! Hold on one sec. All right, there we go. My bad. Yeah, so the forward direction just comes from the fact that the exponential function is well defined. Well-definedness of a function becomes really important when you start constructing your own functions. But what it really means is it doesn't matter what representations you have of these two numbers, this will still hold. Representation might be kind of abstract. Let me make it more concrete. For example, the number 1/2 is equal to 2/4. So well-definedness says it doesn't matter if you use 1/2 or 2/4, you still get this result. That's what well-definedness is, all right? Now, this direction, going that direction, it follows from the fact that the exponential function is 1-to-1. I didn't mention it, but if you take a look at those graphs, you'll notice that the exponential function is 1-to-1. In fact, it's continuous also. It's a 1-to-1 continuous function, any exponential function, all right? So the utility of this proposition is what I said earlier. It allows us to exponentiate both sides of an equation, or it allows us to go from this side to this side, which is what we're going to see in a few examples right now. All right, so here's the first one, and you can try it on your own. I want you to try to solve this exponential equation for x, okay? Think about it for a minute. Okay, verbalize something, give yourself something to think about out loud. And now work it out on your own. Try to solve for x. Your final answer should look like x equals something, and then we'll do it together. All right, here we go. Um, so let's write it out this way. One thing that I notice about 81 is that I can write it as 3 to the fourth. 81 is equal to 3 to the fourth. And now we have exactly the scenario that we saw in that proposition a moment ago. We have 3 to some power equals 3 to some power. And that proposition says, hey, you know what? You can drop the base. You can drop the base on that. And then what you're left with is just the exponents. X plus 1 is equal to 4. That's the power of this that proposition. So if the bases are the same, you can drop the base, and then you end up with this. Now we've just got a good old linear equation. We can solve it using those techniques we learned before. We get x equals 3. Okay, now let's check. Let's just be sure. Let's talk about checking this for a minute. If we plug 3 in for x up here, we get that it is actually valid. So 3 to the 3 plus 1 is 3 to the fourth. 3 to the fourth is 81. Check, that's good. Another way you could think about this particular example is this is an exponential function and this is a positive number. So because the range of any exponential, well, this type of a function here, it's not vertically shifted or anything. The range of this is 0 to infinity. There must be a solution, and it's going to be a valid solution. It's basically, geometrically speaking, wherever this graph crosses the line y equals 81. So let's take a look at that right now. Let me pull that up on Desmos. Where are you? There you are. And let's get some geometric intuition for this algebraic result. We're looking at example 7 here. This is the graph of y equals 3 to the x plus 1. I've got it graphed in blue right here. And then here's the line y equals 81. You can't see it yet because 81 is way up here. There it is. Okay. There it is. Y equals 81. Where do those two graphs intersect? Right at this point when x equals 3, which is exactly what we just found algebraically, right? 3 to the 3 plus 1 is 81. And that's what it looks like geometrically. All right. Okay. Let's do the next example. Kick things up a notch a little bit here. Just like before, I want you to solve this exponential equation. Try this one on your own also, and we'll do it together. You can think about it for a minute. Right. Talk about what you might do first, and then work it out on your own. See if you can solve for x, and we will do it together. Okay. All right, let's do it together. We're going to use a similar technique to what we did before. And maybe I realize I should mention something here. If you have seen this stuff before in the past, or if you've already learned about logarithms and things like that, we don't know about logarithms yet. So at this point in the course, we don't know logarithms even exist. So you cannot use any laws of logarithms or properties of logarithms. You can't bring logarithms in at all yet. That's the next section. So we're just going to do what we did before. We're going to use what we have so far. We're going to rewrite these bases. These aren't the same base. So we can't use that proposition yet. We can't drop the base yet. The bases have to be the same in order for you to drop the base. All right. So what I'm going to do is rewrite 4 as 2 squared and rewrite 8 as 2 cubed. And then I'm going to use properties of exponents. Remember, these will multiply up there. Those will multiply up there. We're going to get that this is 4x minus 2, and this is 3x plus 9. Now the bases are the same. 2 and 2, we can drop the base. And then we've got just the exponents equal to each other. Good old linear equation. We know how to solve it. Move things around, isolate x, and you get x is equal to 11. All right. Now let's check and then let's look at a picture of it again. So one thing is, I'll say this. I'm actually going to use, well, okay. I plugged in x, I'm sorry, I plugged in 11 directly for x right here. Then I did kind of the same manipulation I did before. I rewrote 4 as 2 squared and 8 as 2 cubed, just to kind of make the arithmetic a little bit easier. 2 times 21 is 42, and 3 times 14 is also 42. Real quick, if you can't see that 3 times 14 is 42, remember those techniques we talked about in chapter 1. What's 3 times 10? 30. And what's 3 times 4? 12. What's 30 plus 12? 42. Yeah, there you go. Break it up into those chunks. So this is actually correct. Now let's look at it on Desmos here. Oop, that's not it. Come back. There you are. All right, so let's look at it on Desmos. Now we're looking at example 8. Let me go back down. Here we go. Um, Oof. Wait, what did we come up with? The answer was 11, I think we got. Okay. So here we have in blue y equals 4 to the 2x minus 1. In red, we have 8 to the x plus 3. And we found they met when x is equal to 11. This is going to be hard to visualize because I don't know if you can see how fast these are growing, insanely fast. X is 11 is way out here. Um, I don't know if I'll even be able to scroll high enough for it to show us the answer there because if you remember, let me flash back. The answer is 2 to the 42, which is a really big number. And 2 to the 42 is a really big number. So I don't even know if Desmos will allow us to zoom out that far. I suspect that it will not. Um, but one thing we could do is this. We could do this. Let's just be a little clever here. We're going to say f of x equals 4 to the 2x minus 1, okay? This is the same as that blue graph. I just wrote it as a function. In fact, I could have just done this. I should have just done this. There you go. F of x is equal to that. Let's just make it a function and let's evaluate it at 11. F of 11 is, oof, there you go. So here it's actually giving it to us in scientific notation. It's 4.398 yada 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 times 10 to the 12th. So what is 10 to the 12th? Here, think about it. What's 10 to the 12th for a minute? Hmm. 6 is a million, 9 is a billion, so 12 is a trillion. So these graphs will intersect, but they won't intersect until x equals 11. And when they do, the output value is going to be about 4 trillion. That's where they'll intersect. Wow. Okay. Oof. All right. So let's try one more example here. One more example. This one. All right, here's another one I want you to try. Try to solve this exponential equation for x, use properties of exponents, and so on and so on. So I'll let you think about it for a minute. All right, verbalize something, give yourself that feedback, and then go for it. Solve that equation. Okay, let's do it together. All right, so we're just going to massage things. The goal is still the same. We need to try to isolate x in some way, but we're going to use properties of exponents first. So we're going to massage this a little bit. We're going to write x times 2 as 2x. 1 over e cubed is equal to e to the negative 3. Now we're going to combine these two expressions using properties of exponents, 2x minus 3. And now, check it out, we've got exponential equals exponential. In this case, the base is e. So because the base is the same, we can drop the base. Boom. And then we're left with this. Now we've got a good old quadratic equation. And we can put everything to one side so it's equal to 0. And I hope you remember how to solve these things. Remember, there's 3 ways: factoring, completing the square, or the quadratic formula. In this case, these numbers are nice enough. So because they're nice enough, when you factor it, you can factor it over the integers, and you get that x is equal to negative 3 or 1. And that's it. We're going to check our work again here, but I think what I'm going to do is, yeah, I started a little bit down the line. So to get from here to here, we used equivalent operation. We kept the equivalences. So this is equivalent to that. And I'm just going to plug in our numbers to this equation just because it's a little easier to do rather than having to manipulate everything from here, okay? So I'm going to plug in negative 3 for x right here, right here. And then when I simplify, I get e to the negative 9. Check, that's a solution. Then when I plug in 1, like so, I'm going to get e to the negative 1 equals e to the negative 1. Check. So there's two solutions. That means, geometrically speaking, this graph and this graph are intersecting at 2 points. Let's take a look at it on Desmos here. All right, let me hide this. Let me get rid of that for a sec. Hide example 8. Let's look at example 9. So here, let me do this one at a time, zoom in a bit. So this is actually the graph of e to the negative x squared. This is a really important graph. You'll talk more about it in calculus, but this is the Gaussian. So this is a function that you will pay a lot of attention to in calculus. And if any of you want to go into probability or risk analysis, this is basically what you're going to study. You're going to study a lot of this in terms of it's a probability distribution. So I'll just leave it at that. But you can kind of see it's got this hump in the middle here. It's the bell curve, right? So if you think about what the bell curve looks like, this is the best bell curve in some sense. Now let's look at this function. There we go. So this looks more like a standard exponential function, right? And in fact, if you were to basically mush these together, you would get an exponential function, just as we did during our solving process. But it says, what did we find? They intersect at -3 and 1. Okay, I can clearly see they intersect at 1, right? They're intersecting right there at the number 1. It's hard to see, but they're also intersecting at -3. I'm going to zoom in. It's hard to see, but they are intersecting there. I wonder if I can zoom in if it'll actually show us a difference. I don't know if, oh, there it is. There it is. You see, they're not intersecting here, but the moment we see down here, this is like, oh, you can't see it all the way down there. Maybe I can bring it up a tiny bit. Hey, hey, come here. Come here. Come here. Tiny bit. Ah, there we go. Right down here, you can see that it says 2.999972. If we keep going this way and get to 3, you'll see they intersect. Oof. Just counting up, we're getting closer. 99999999999991. Almost, almost. And look, the lines are getting closer and closer together. 9889993. Oh, and that's where they intersect. This point, right where they intersect. Actually, here, Desmos is having trouble properly displaying the intersection point because these graphs are so close together. We're starting to get into issues of tolerance with what Desmos can actually physically, what Desmos can actually computationally do. We're starting to starting to get outside of tolerance here. Okay, but that's what it looks like. That's why it's good to consider the geometric interpretations of these things. All right, back to the slides. On that note, let's play. So that's it for exponential functions for now, but we're going to explore more in the activity. You can always mess around with these things in Desmos. I always encourage you to use Desmos to graph these solutions and graph these things just to give yourself more experience with those, okay? But I'll end it here, and I will see you next time when we talk about logarithmic functions, all right? Have a good one, everybody. Thank you again.